This is lesson 5 on linear models. I'm on page 43. So we're going to talk about sequences and what linear model y equals mx plus b can we arrive at given the sequence if the scatter plot is not linear, if the scatter plots do not all lie on a line like we looked at with arithmetic sequences. All right, so if you're on page 43, there are two scatter plots, figure 1.5-1a and 1.5-1b. Looking at those scatter plots, because the figure A, that scatter plot is more tightly around what would be a line, then that model would be a better fit for a line, a y equals mx plus b, than figure B. So there's a method that we can use. There's two methods that we can use to determine if a linear model is the best fit, because the scatter plot could look like a parabola, it could look like a cubic equation, but we're going to use the data to determine if in fact a linear model is the best fit. We're going to use our calculators a lot. All right, so following me to the next page, we can look at the finite differences. The finite differences are literally just the change in the y values. So I've written the data from example 1 on the board. All the finite differences, all that is I take successive consecutive y values and I subtract them. All right, so the year is my x value in example 1, and the cash flow is my y value. Literally, I take 2.79 minus 2.38, and this is my finite differences. And I've gone ahead and calculated them. So the difference is 0.41. If I take 3.23 minus 2.79, that's 0.44. If I take 3.64 and I subtract 3.23, I get 0.41. If I take 4.06 and subtract 3.64, I get 0.42. Notice my finite differences are very close to the same value. When we look at a set of data and our finite differences are very close to the same value, that means they're edging up that first quadrant at the same rate. And when my finite differences are close to the same value, then a linear model is the best fit. So that is one method of deciding if a linear model is the best fit. You look at the finite differences, and if they're all close to the same value, then you can determine that yes, a linear model is the best fit. Okay, finite differences, first method. The second method is when we look at the residuals. All right. Now, what is a residual? So I've graphed the first few of these values. Remember, when we're talking about years, we always say the first year is 0. So the x values would be 0, 1, 2, 3, 4. So 0 would represent year 1988. 1 would represent year 1989. All right. So for 0, I plotted 2.38. And I've plotted all the points to show you what the residual is. And I've drawn a linear model sort of in the middle of the scatter plot. All right, so the residual is literally the difference between the y difference between the actual point 1, 2.79 and the difference between what that point is, that y value is on the line. All right, so it would be here to there. That is the residual. It's when we're going to square them to take the negatives out of the equation. All right, so this would be a positive residual, right? And this, if I have a point up here, it would be a negative residual. Actually, this is a positive residual because the point lies, so all of these are positive residuals, taking back what I just said, because the point lies above it. And these all below the line would be negative residuals. Okay? All right. I want to look a lot at example 2. So I'm going to erase the board and write. So get your calculators ready, because we're going to find the equation of a line. All right, so we're going to let our advertising expenditures, I'm going to write money, be our X value. So we have just 0 through 6. 0, 1, 2, 3, 4, 5, 6. And then we're going to let our sales revenue be our Y value. So if I were putting this in stat edit, this would be list 1, this would be list 2. And I'm sure these are in, this is in hundreds, this is in thousands, okay? The table gives me that information. 1, 2, 2, 3, 3, 5, 5. So if I were plotting these, so now turn to page 46. If I were plotting these, it would be 0, 1, 1, 2, 2, 3. That is the actual data point that I would plot. All right. So if you're on the top of page 46, they pick 2 points. And come up with a model. They calculate the slope. So that's from the previous lesson, right? We can take any 2 points, 2 coordinate points, come up with a slope, and come up with an equation of a line. And so the equation that they come up with, they use 3, 3, and 1, 2. So they use these 2 points, 3, 1, 2, and 3, 3, to come up with an equation of a line. All right? And what do they come up with? They come up with y equals 0.5x plus 1.5. And they plug in the x values into here. And then they come up with the model point. All right, so when they plug in 0, they get 1.5. When they plug in the x value for 1, they get 2, because 0.5 plus 1.5 is 2. When they plug in 2 times 0.5 plus 1.5 is 2.5. You can just follow the table, right? When they plug in 3, they get 3, because that's a modeling point we use. So the points we use to calculate the slope, to come up with the equation, those points should always be the same. And I'm just going to copy the table from there forward. 5, 4, 6, 4.5. All right? So the residual is this y value from the model point minus the y value, right? That's the residual. Remember, the finite differences would be 1, 2 minus 1, 2 minus 2, 3 minus 2. We're not looking at finite differences. We're looking at the residuals to decide if it's a best fit. So we're taking this is my, would be your x, y, and they're calling this y value your r. So we subtract, I'll get a different color. We're subtracting this value minus that value to get our residual. Actually, it's the opposite way. This minus this. So we're going in this direction. The actual plot, which is what I said earlier. The actual plot minus this y value. And that's going to be our residual. All right, so 1 minus 1.5 is negative 0.5. 2 minus 2 is 0. 2 minus 2.5 is negative 0.5. 3 minus 3, 0. 3 minus 3.5, negative 0.5. 5 minus 4 is a positive 1. 5 minus 4.5 is a positive 0.5. And when you add them all up, you get 0, right? Because 1 cancels those two and 0.5 cancels that one. So the sum of my residuals is equal to 0. When the sum of your residuals is very close to 0, then we can say that that linear model is a good model for this data. Okay, so we've looked at two. We've looked at the finite differences. That's a change in the y values. When it's close to the same value, a linear model is the best fit. When we look at the residuals, what's the residuals? That's the actual y point for the actual data minus the y value on the model, the linear model. When we add all those up and it equals 0, then we can say that this line is a good fit for the data. But there's another way, residuals squared. When we eliminate the negatives, and this is actually the best way. Well, the best way, we're going to do it with our calculators. When I square the residuals, so when I take the residuals and I square it, I get 0. So I'm eliminating the negative impact. And I'm just copying it. When I add these up and I come very close to 1, then that is in fact the best fit. So look what they do at table 2. They pick a different model. Just follow along with the table on the bottom of page 46 with me, okay? They pick a different model. They pick different points. It's model B. And they come up with y equals 0.6x plus 1.4. And they get the model point. They calculate the residuals. They add them up. Notice the residuals. It's negative 1.4. So that, if I were just looking at the residuals, model A is a better fit. Okay? But the better method is to look at the residuals squared. And when we square the residuals and add them all up, and this value is close to 1, then that is in fact a better model than just the sum of the residuals being 0. And notice in that model B, the sum of the residuals squared is 1.56. So that line, y equals 0.6x plus 1.4, is actually a better model than model A. And if you look in the figures, the top figure that's to the left of the model data, the line actually drawn, 1.5-4 is not as good a fit as the one on the bottom, 1.5-5. So actually when we square the residuals, then that is a better fit. All right? So look at example. We're going to actually work through all of this with example 3. All right, look at example 3. Let's look. We're going to draw. It says draw a scatter plot. All right, so we're going to go into Stat, Edit. If there's something in your list, right, you're going to go up to List, hit Clear, and go down. That's how you clear it. Go up, hit Clear, go back down. All right, I'm going to put this information in my calculator. So my list 1, which is going to be my X values, is going to be 3, 4, 5, 6, 7, 8, 9. Must be triangles, huh? Yes, triangles and radius. All right. And in the second list, I'm going to put the radius. So 0.577, 0.707, 0.851, 1, 1.152, 1.306, and 1.462. All right, so I have my lists in, and I could do a scatter plot. I'm going to go ahead and do the scatter plot. All right, so I'm going to look at my window because that's always important. What is my smallest X value? It's 3. My largest X value is 9. So I'm going to go 0 to 10. My smallest Y value, okay, these values, Y values are so incrementally small that I'm going to go 0 to 3. I want to be able to see it. All right, and so when I graph it, this is what I get. It actually looks like a great line, right? You would think a line would fit it. All right, now if I were to calculate the finite differences, I'm just going to look at my Y values, okay? Only my Y values. So I have 0.577, 0.707, 0.851, 1.0. I don't know why they wouldn't put 3 because they all have 3 decimal places, 1.306, 1.462. So my finite differences, all I'm doing is taking 0.707 minus 5.77, and that is 0.13. I take 0.851, subtract 0.707, and that is 0.144. 1.1 minus 0.851 is 0.149. That's 0.153. That one was easy for me to calculate. Oops, I wrote number 7 wrong. This is actually a 2. So this is actually a 2. 1.306 minus 1.152 is 0.154. 0.156. They are all close to the same value. So I would conclude that a linear model would fit it. Now, looking at the finite differences just tells me, does a linear model fit it? It doesn't give me a linear model. All right, so we're going to use regression on our calculator to actually calculate what the y equals mx plus b model should be. But first, I need you to do something. So I'm going to second quit to get out of that. All right, I need you to go to second 0. and you're going to have this list. I need you to go to down to diagnostics on, or else it's not going to give you all the information that you need. So what did I do? Second, 0. And now I'm just going down till I see the words diagnostics on. Getting closer. That's diagnostic off. Okay, when my arrow is at diagnostic on, I'm going to hit enter, and it's going to come on my calculator. I'm going to hit enter again. And it's turned my diagnostics on. All right. We've got our list 1 and our list 2 in. Okay. So you have to have your list 1 and list 2 in order to come up with a linear model. All right. Remember what they did in the previous example. They just took the slope of 2 points and calculated a line. Then they took the slope of another 2 points and calculated a line. They looked at the residuals and they looked at the residuals squared to decide which is the best fit. Your calculator will do all of that for you. All right, so here's how it goes. You're going to do stat and go over to calc. And if you go down to number 4 is linear regression. And then you hit enter. It tells me my X list is list 1, my Y list is list 2. I'm just gonna, as long as you're list 1, list 2, and you should, we're gonna go down. I'm just hitting enter, 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 and now I wanna calculate. And it gives me this model. It's in Y equals AX plus B. Here's my A value, here's my B value. So it's Y equals 0.1482, I'm reading this backwards, 0.1484 X plus 0.1177. That would be my linear model. I'm going to write that on the board. So the linear model of best fit is Y equals 0.1484x plus 0.1177. That's the model. Notice what it does for you. It squares the residuals. That's why we turn the diagnostics on. Otherwise, you would not have the residuals squared, or you would not have the sum of the residuals. That is very close to 1. That means that this model is the best fit when this is closest to 1. The correlation coefficient is your R value. When it's close to 1, and it is, that means that this model is the best fit. It's a very good fit for the data. All right, so here's what we're gonna do. We're gonna go in and we're gonna put this model in Y sub 1. I'm leaving my plot on. Oh, I'm already in Y sub 1. All right, so I'm going to put 0.1484x plus 0.1177. All right, that's what I put in Y sub 1. So now when I hit graph, you can see that it's a great model. All right. Now look at example 4 on page 49. This is a very long example. In fact, what I might do is, instead of doing that, I'm going to make another video of a homework problem. Okay? But we've gone through the steps. If you look at your homework, actually I'm going to make another video for your homework. All right.